Hello guys, this is Mayank explaining my Splitwise clone made up using Java Spring Boot. Okay, I want you to consider a situation in which a group of friends goes on a tour. Let's say Alice, Bob, Charlie, and David goes on a tour. And in this, Alice made a payment of $100. It can be of anything. Let's say Alice made a payment for hotel. So these $100 will be split among all his friends present at that time. It will be Bob, Charlie. Let's say somehow David was not present at that time. His split was not meant to be counted. Then Bob made a payment. It will be split among all those friends who were present at that time. And Charlie made a payment. It will be split. So the main question arises is who pays who and at last, right? So to fix this problem, we can just first create a graph. We can represent this scenario in a graph, right? Like Bob pays Alice 33, Alice to Bob 30, and Bob to Charlie 30. So we can represent it via multi interconnected graph. So to find out who pays who, how much at last, the first brute force way is to traverse the graph all along, right? I will go to Bob. Hey Bob, you paid Alice 33. Alice made Bob a payment of 30. We will count that, then that, then that. So it is a very highly inefficient process, right? Let's say if my graph looks like this, it is a very much complex graph. So I can't just go to each and every node and then traverse, then count. It will be a very highly redundant way, right? So we have to come up with an optimal solution for this, and the optimal solution is greedy splitwise algorithm, right? So the key point in this algorithm is that I don't store who pays who. I only store what is the net balance of each user after all the transactions. That basically means is that Bob paid Alice 33, Alice gave back Bob 30, then Alice demanding Charlie 33. After all these calculation, payment made, payment done by Alice, I'll calculate the net balance of Alice. That comes out to be 36.67. The positive sign is denoting that at last Alice wants money, and this negative sign is denoting that Bob has to give money. Right? We don't know to whom they have to give. We only know that they have to give money to someone and they have to take money from someone. Then in the next step, we'll store all the creditors that the guys that are demanding money in a max heap. This is the max heap, and the guys who are giving money, the debitors, we'll store them in the min heap. Right now, the next step is I will just pop the first element, that the topmost element, the guys with the maximum balance. We will settle them out first. Right. So Bob has $33 to give. So he gives all his money to Alice, and Bob then goes out of picture. So Alice has wants 36, but he's only taking $33 from Bob. So Alice still wants $3.33, right? So we will calculate this as a transaction. Bob to Alice, $33.33. You can see it right there. Bob to Alice, $33.33. Then Alice will be shifted downward in heap because it's in priority queue, right? Charlie will be pushed upwards. Then again our algorithm will work, and David will pay back money to Charlie because those guys are on the top of the heap. But Charlie only wants $26 from David, so Charlie will take his share out and goes out of picture. Then my David reduces to minus 3.33, right? And we will store that as a transaction as well. You can see David to Charlie 26.67, and then at last my David will pay his share back to the Alice, and the net comes out to be 0. All the transactions are made. This will also be stored David to Alice 3.33. You can see it right there. Okay, so the time complexity of this approach comes out to be O and log n. Log n is to store the elements in the heap because it's in priority queue, right? So I have to sort them as well. And n is the number of elements. Finally, we have our transactions right here. The optimized transactions come out to be 3, time complexity O n log n, space complexity O n, and the possible transaction 6. Sorry guys, I don't think it's right. Basically, I used Claude to generate this algo visualizer. This possible transaction and this efficiency fields are not right. Because see now that we have 1, 2, 3, 4, 5 maximum possible transaction in this scenario, And I guess that 6 is coming from the picture where every node is connected to every another node single time. Yeah, yeah, yeah. That basically means every user pays every another guy only a single time. Then it comes out to be 6. I guess the formula was n into n minus 1 by 2, basic graph traversal. Another thing I want to share with you guys that there is a lead code problem, lead code 465, optimal account balancing. It is very much similar to our scenario, but it requires us to find out the minimum number of transactions. That's the catch here. So with this catch, this problem becomes an NP hard problem. I guess you guys know what is an NP hard problem. A problem is called NP hard when we don't know if there is a solution exists from for that problem that can solve it in polynomial time complexity, right? So we'll use dynamic programming and backtracking to approach this problem. I mean, we can solve it only backtracking as well, but DP helps us to optimize the runtime. In this scenario, the complexity comes out to be O2 raised to power n. This is an exponential time complexity. So we could just can't use this approach in our solution, right? So we'll come up with a trade-off. We'll say, okay, no matter what, no matter if we don't find out the minimum number of transactions, right? If we are coming with an optimized transaction within a very highly efficient time, we are good to go with it, right? We don't matter, it don't matter to us if it's minimum transaction or not. If it's fast, it works for us, at least in real world scenarios. So that was the algorithm part. Now that next up is system architecture, diagram, basic JWT cookie based authentication, and basic CRUD applications, create, read, delete, update, post mappings. You guys know about it. And this my program runs on MVC architecture. I want thing I need to mention it. MVC architecture, model view controller, monolithic architecture. And then we have our database diagram, four entities: group, user, expense, the guy who made the expense, and expense split the expense which is splitting into the guys, it is storing that. And then at last we have our algorithm. First I will store all the net balances of each and every user after all the transaction. This happens at the runtime, guys. We don't store who pays who. We would just actually we calculate it at the runtime. We calculate the net balance and then at last feed it into our algorithm. And that's it, guys. And the at last this is a Postman external APIs. Another thing I want to share with you guys is this. This is my own documentation I made up while building this project. I thought it would be cool to showcase actually what I did, right? So first I created the UCL mappings from all these entities I need to have as per the problem statement. Then I have to come up with this optimized solution for a problem. So this optimal transaction finding question, the lead code one, I in fact did solve it in the past, but again that was of 2n. So I have to come up with this greedy approach. Well, basically, I did not come it up with by myself. I used AI and stuff to come up with the solution. But yeah, I got to learn a new pattern that this problem can be tackled via greedy approach and can be solved in O and login. I mean, not exactly this problem as we are not finding the minimum number of transactions, but yeah, still. So this was my certificate of authenticity, I would say, and thank you for listening to me. Thanks.